Okay, I think we shall start now.
Okay, please do.
First of all, I would like to say hello from Thailand. I think there are some attendees might come from different time zones. Or okay, I want to introduce myself. My name is Virachai. I am your local host for the tonight or maybe 2 days. It depends on your time zone, right? Seminar. So on behalf of the local organizing committee, I would like to welcome you to the this RMRC Pre-RoboCup event. Tonight we have Professor Raymond Che with us to talk about rapidly manufactured robot challenge, which is actually a sub-competition of the RoboCup Rescue League, right? Also, he will give us some overview of the rules and logistics of the competition. Okay, before I start, I would like to introduce Professor Raymond to you. Professor Raymond Che got his PhD degree in robotics, machine learning, artificial intelligence from the University of New South Wales. So no doubt he is an expert in this field. He is currently the research professor at Georgetown University in Washington, D.C. He is the board of trustee of the RoboCup and I think has taken care of the RoboCup Rescue League for I don't know, maybe for a long period of time, right? And the sub-league RMRC. Okay, please welcome Professor Raymond. Okay, Professor Raymond, it's all yours now.
Okay, well, thank you, Virachai, for the very kind introduction, and thank you everyone for coming to my my presentation about the Rapidly Manufactured Robot Challenge for 2022. And this is being presented on behalf of the overall committee. Speaking of the overall committee, we have myself, we have Amy, Archer, Gerard, Graham, and Adam. Adam being the founder of the RoboCup Rescue Robot League, under which the RMRC is based. And then, of course, with many thanks to the two local chairs for this year in Thailand, Virachai and Panavi. I hope I got the pronunciation correct there.
Yeah. Panavi, yeah.
And I have, and of course, here are all the people who participated in the RMRC when it was last held in person in 2019 in Sydney, Australia. So to introduce the challenge itself, so why are we doing this? So ultimately, this is because emergency responders need robots with assistive and autonomous capabilities to perform extremely hazardous tasks in complex environments from safe to standoff distances. The overall league of RoboCup Rescue, including RMRC, the goal is to provide a tangible language between which the researchers, manufacturers, and emergency responders can communicate to refine their implementations, to measure and to highlight breakthrough capabilities. What we're trying to do is we're trying to avoid this kind of situation here, where a person in a bomb suit needs to walk past a perfectly operational robot and do its job because they know that the robot can't do the job. Okay, we want to advance the state of the science through measurement science so that the requirements that the people who are putting themselves at risk, those requirements are properly conveyed to those building the robots, designing the robots, developing the next generation, so that this kind of thing doesn't have to happen again. And this actually is very close to home here in DC. This is actually at Dulles International Airport, just outside Washington, DC, the main international airport in the DC area, with a suspicious vehicle. Robots should be doing this. We shouldn't have people walking up to these. So what is the RoboCup Rescue approach? The idea is that you're using measurement science to measure and highlight breakthroughs. So RoboCup Rescue works with the broader DHS, NIST, STM International Standard Test Methods for Response Robots program in order to help develop reproducible test methods that are cheap and easy to conduct. Every year, we build the arena, which consists of a whole bunch of these standard tests for robot performance. We also build prototypical tests. We refine them at RoboCup. We get the latest implementations, interesting technologies to run through these to make sure that the test methods are still relevant. We measure combinations of existing capabilities and emerging technologies. The idea is that you, as the researchers, the students, are coming up with very interesting solutions to these problems. We want to measure how much better they do compared to what's available to the responder out there. We then want to use the tests to communicate what isn't being done well out in deployed and purchasable systems, to inspire innovation and to help find ways of addressing the gaps in capabilities. And then once these capabilities are commercialized, these test methods guide the purchasing and deployment decisions using statistically significant data. Also, once they become available, they focus training with repeatable tasks to measure and compare proficiency in order to make sure that the human element is also working with the robots, and then identify readiness issues with equipment and or training, and then to further develop new test methods to highlight where these gaps are. And we've been doing this for a long time. This started in 2000 at the AAAI conference in Austin, Texas. And last year, of course, was held online worldwide. Okay, so there are communications to facilitate communications. RoboCup specifically is very useful for responders and manufacturers to learn about emerging technologies, and also to identify groups and individuals, students, who are doing particularly well, who have interesting ideas, interesting technologies. The researchers learn about the gaps, and the local responders in each area where we do RoboCup get to keep the tests after the competition and use them to develop their own test facilities. In 2019, when it was last held, half of the arena went to the New South Wales Police. The other half went to an organization called EPE, which has turned it into a test site as part of its broader test facility. Interesting thing about the New South Wales Police, who worked with us to build the arena, is that they not only run their robots through it, but they also run people through it in their bomb suits. We'll talk more about that later. So, introduction of the RoboCup Rescue Robot League overall. So, development and validation of standards. They evaluate robot capabilities across mobility, dexterity, that is manipulators, exploration, mapping, and through that, human factors, that is how a human interacts with the robot system, and sensing. The overall league has scales, has these different scales, 120 centimeters, 60 centimeters, and 30 centimeters. Within RMRC, we're only interested in 60 and 30. And they have individual tests laid out first for testing of specific capabilities, and then sequenced in the finals. More specifically, the preliminary rounds consist of the standard test methods performed individually. The teams select which ones to run with scores that are normalized to the best performer in each test. The best performing teams qualify for the finals, where the tests are made harder and sequenced together. And the championship is awarded for the best performing team in the finals. However, we also have best in class and technical awards for the best performance in specific suites of tests during the preliminary rounds. The idea is that a team that has a very interesting or very good specific capability that they've been working on, but might not be able to integrate a solution for to win the entire challenge, can still win awards for their specific area of expertise. The competition itself, we have more than 300 test trials conducted every competition due to massively concurrent scheduling of time trials and the use of teams to proctor each other. We can focus on their own research goals, and the rest we've already mentioned. And here we have the robots from the Rapidly Manufactured Robot Challenge in 2019, alongside and around one of the robots from the New South Wales Police. And of course, one of their bomb suits in the background that we actually had one of them run around in the arena with. Now, of course, the robots can look similar but perform very differently. This is why we need statistically significant standardized tests, so that we can measure what the differences between the robots, how that affects their performance and affects what they're useful for. A lot of the robots started out from a standard design that we put out called the Open Academic Robot Kit. In fact, that's why the URL of the challenge start is comp.oarkit.org. But the idea is that it's open source. that we can have teams build it and then improve on it. We'll talk more about that later. This also allows us to compare scores across various suites of tests. This allows us to not only figure out who is the best, but also to determine if maybe the best robot overall isn't the one you want because you want specific capabilities. For example, in 2019, iHammer Go was the best in terms of all of these capabilities. It has the biggest radar chart. But maybe if you're interested in dexterity and sensors, then this robot here, which isn't the best overall, but has specific capabilities in those directions, is the one you want. This means we can make robot selections based on statistically significant data. So let's talk a little bit about the test lanes. We have the 120 centimeter scale. This represents parking lots, public buildings, areas which are subject to requirements for getting wheelchairs through, for instance, are built to this kind of scale. This is where the larger robots play. We don't use this in Rapidly Manufactured Robot Challenge just because building robots at this scale tends to be a little bit hard for rapid prototyping equipment and a little bit more expensive for high school students. 60 centimeter scale represents things like dwellings and public transit. Note that we're not scaling down the challenge. We are tackling the full-size challenge at a smaller scale. This is still very much full size, and there is definitely a need for this. 30 centimeter scale is where most of the action is at Rapidly Manufactured Robot Challenge. Here, we have an emphasis on 3D printed and rapid prototype robots. And this now represents confined spaces, cluttered indoor areas, collapsed buildings, things like that. So why the Rapidly Manufactured Robot Challenge? The idea is to lower the barriers of entry, the technical, financial, and the infrastructure into space. The idea is that these robots can be built very cheaply for a few $100s. They don't require, in order to build the robot, you don't require much more than the ability to assemble flat pack furniture. You need some spatial awareness and the ability to follow directions, but to get a basic robot working based on the design, the open source designs that are out there, you don't need to be an expert in order to actually get the robot together. But then you can improve it in the specific areas of where you have expertise. You also don't require very much infrastructure and space. The 30 centimeter scale arena can be built and laid alongside the side of a room, a classroom, or a workshop, and doesn't take up very much space without having to pack it away each time. We also want to promote the development of open source resources, 3D printing, laser cutting, and desktop CNC milling. The idea behind this is that it makes it very easy for teams to open source and share not only their software, but also their hardware. We want to facilitate the use of robotics in science, technology, engineering, art, and mathematics. All of these together, including the art, are critical in building useful robots. And then ultimately, we want to develop a library of low-cost designs that are tested to statistical significance and can form the first rapidly manufactured, low-cost disposable robots that become available to the first responders. What we then did to further lower the barrier of entry is we brought the RMRC under RoboCup Junior. We are still playing in the major arena, but now students can enter paying the junior fees, registration fees, and going through the junior qualification process. This does mean there is an age limit on the students, but we say nothing about the mentors. And the Rapidly Manufactured Robot Challenge is one of these strange ones where it's okay for the mentors to do some of the work, as long as the students are driving the robots and the students have a working knowledge of the system as a whole and a specific expertise in whatever it is that they contributed to the challenge. So a hybrid competition organization. We have to be a little bit realistic this year. We hope that we can all meet in Thailand, but we understand that some teams, because of their local situation, may be not allowed to travel, but they still want to compete. So this year we're having a combination of both the remote, online, and in-person competition. The power of the standard test methods means that the individual tests in the preliminary rounds are directly comparable between remote facilities and the in-person championship. The remote teams will therefore be eligible for some of the best-in-class awards. but only the in-person teams can participate in the finals, where things actually have to be judged live and in person on the same arena. So the qualification process, and this is in addition to the junior qualification requirements, such as the age limit and so on. So for the in-person competition in Thailand, the teams need to declare their intent to participate via the mailing list at group or groups.oarkit.org, and you need to do this soon. We'll want to hear from you probably in the next week or so. The preliminary team description materials, or TDM, describing their entry is due by the end of February. Most teams will need to include videos of their robot doing at least 2 tests. An updated team description material describing their entry is due 2 weeks prior to the competition. This is scored a little differently. It's scored based on how well it helps another team learn something new that's useful. The score for the updated TDM is then used as a multiplier for the preliminary rounds. This encourages the sharing of open source capabilities, and we'll talk more about that in a minute. Now, for the online competition, all teams are welcome. Please declare as soon as possible. But if you're not intending to participate now and then later on find that you can participate, that's still okay. Teams then submit their video packages with their updated TDM. And this has to be done by a deadline that will be announced in due course, probably a month or so from the competition. So the qualifying videos. By the TDM due date, all teams must submit videos no more than 1 competition year old, so 2019 is valid for this year, of a robot performing in at least 2 tests. This is just to ensure that the team has the ability to actually put a robot together and run the tests. Doesn't need to be the same robot you'll compete with. We realize that in the intervening months, the robot's performance will improve. You'll make changes and so on. This is just to make sure that we know that you can get a robot together. Now, we realize some very new teams may not have a working robot and may have to skip this requirement and be judged only on their TDM. But this needs to be for teams that are completely new. Existing teams are expected to have something together or to put something together that can at least perform a couple of the tests, knowing that these won't be their final performances, of course, that you'll improve the performance. Here's an example of what a qualifying video looks like. This one is from Major Rescue. We want these quad screen setups where we can see both what the operator is seeing, what the operator is doing, as well as detail and overview of the task they're performing. And this can be put together using hardware if you have a quad box, or you can put it together after the fact using 4 cameras that are recorded and stitching them together afterwards using any number of programs. And we have tutorials online how to do that. The team description material is for qualification, has a particular set of information that we expect, and details of this are online. The updated team description materials is a little bit unique. And again, this is scored based on how well it helps another team learn something useful. And it becomes a multiplier for the preliminary score. So this is something that you'll want to, that is a critical part of the competition. This is to encourage teams to share their knowledge and contribute to an open source body of work. These have to be open source under some kind of permissive license, such as Creative Commons share alike. Topics that we've seen include things like how to build the robots, software setup, and tutorials on subjects such as inverse kinematics. These are all very welcome. And eventually, once we go back to fully in person and we can travel, these will tie into the Rescue Robotics Summer Schools, which are opportunities to come together and learn from each other outside of the pressure of a competition. We encourage you to visit the website comp.oarkit.org, where you can find links to the 2019 updated TDMs in order to, if you want to come up to speed or to see what the students have been doing. You'll also find on oarkit.org some of the reference designs that started some of these teams. So what are the test methods that we use? So test methods are standardized basic tests of individual capabilities that are then put together. And we have tests for things like terrain, maneuvering, manipulated dexterity, and sensing. The idea behind these tests, and here are some examples of some pictures of them. Let's look at these first. So here we have a few. We have hurdles that the robot is supposed to go over. And the pipe edges here are particularly challenging to get grip on. We have crossing ramps, we have step fields, we have elevated ramps. These provide different challenges to mobility. Here are some close-ups of those. We also have dexterity challenges, such as extracting pipes, looking into pipes, pushing buttons and keys with some level of precision. We have various sensor tests, object recognition, motion detection. We also have these in distributed form, these QR codes of different sizes that the robots need to see moving around an area. These represent the ability to automatically determine how much of an environment you were able to inspect with your camera, and doing this automatically. We also have surprise elements. For instance, in 2017, we had this loose packing material that was an entanglement hazard that was a surprise to the teams when they got to the arena. In 2019, we had things like mulch that provided a different entanglement. So we keep things a little bit interesting as well for the in-person, even though most of the competition is standardized. We're also bringing on board some search and inspect tasks with these inspection rails, which measure the different abilities to inspect an object, whether you can inspect something that's open, whether you need to get lined up with the opening, such as you're trying to look into a box, and then a confined one where you need to get right up to the opening to see the entire chart, such as you're actually looking inside something. For mapping, laser mapping and 3D mapping, we also have tests. This is laid out in a natural environment like it would be if it was done distributed and remote, where we have these fiducials. These are half-round cylinders placed on opposite sides of a wall, so that if you map all the way around the wall and your map doesn't break, it forms a full circle. Otherwise, the amount that the map has broken can be measured. Now, the thing is that we realize that these tests are not the full game. They're not the full rescue, but they represent basic capabilities that the robots need to perform in order to be useful. It's a bit like for a sports team, when you have new players come in, you don't just play games the whole time, right? You have basic tests, running, jumping, catching, throwing, whatever is relevant to the particular sport and to the particular position that the player will be playing. Based on the performance in those tests, you then start playing test games. Similarly, when you're training, you don't just play games the entire time. You also have basic tests, the same ones, running, jumping, catching, throwing, that are used now as exercises in order to train. And this allows players to target specific abilities that they may need to further develop or improve or to recover from injury. And it also allows the coach to determine what specific areas particular players may need additional training in. That is much easier to do in those specific tests than if all they were doing were playing games, and then now the coach had to figure out what was missing from a particular capability. So, competition logistics. During the preliminary rounds, every day is divided into 10 to 15 minute synchronous time slots. It depends a little bit on how many teams we get to make the logistics work out. And every day, teams take turns selecting which time slot and test to run. All the tests are available, although there is a limit to how many we can run concurrently, just based on the number of referees and judges we have. And this means that we can run many teams through the arena at the same time in the specific tests during the preliminaries where everything is separated. This allows us to get the massively concurrent test trials going. At the end of the preliminaries, for each test, the scores are normalized to 100. This means we can compare really difficult tests where maybe even only one team is managing to complete it, in which case they get 100 because they've done something no one else can, as well as the easiest tests that everyone can do. But now you need to be the best in that test to get your 100 points. These are all then added up for the championship, but they're also added up per suite to form the best in class awards. For the final rounds, the finalist teams work together to arrange the test methods into a maze. Points are then scored for traversing each test once in each direction in a fixed amount of time, depending on how many teams we get. The manipulation tests, drops, and other challenges are then added for more points. We should note that we determine how many teams go through to the finals by looking for a cut in the scores. No one just misses out on the finals. If you're just below what would be the finalists, you become a finalist as well. We need to be flexible about this because we realize that while these are standard tests, there is also a measurement error. So there is some uncertainty. So we make sure that if teams are scoring close, that they're treated as similar. Now, for the online competition, during the preliminary rounds, teams upload uncut quad screen video as they did as the in-person teams did for qualification. Teams need to upload this, performing all of the tests they want to be judged on, to a time-stamped video sharing site such as YouTube, with their own scoring of the tests. The teams score themselves, but they only upload their best run. By the deadline, they also need to submit their team description materials, and we'll announce the deadline in due course. Once they're up there, the teams can now inspect and attest to each other's scores and submit proposals for correction, either up or down. This means that the teams are scoring themselves, but everyone else is looking at their performances and going either, wow, I didn't think that robot could do that. I want to see why. And at that point, you read their TDM. Or they say, oh, you missed a point here. Your score should be this. Or maybe you misinterpreted the scoring and it should be that. So this idea is that we have a very collaborative scoring process that also scales so we can have as many teams online as want to join us. The scores are then normalized as before. We can't directly compare this to the preliminaries for in-person because the in-person rounds, the teams have to just perform during their time slot, whereas during the remote online preliminaries, the teams are uploading their best performance. They may have tried to test 10 times to get the best performance for this. However, the top teams have demonstrated their ability to actually get their robot working well, and they progress to the best-in-class remote finals. The best-in-class remote finals are performed live on video conference with judges and the public before RoboCup week. Here, they now only get one chance to replicate, to demonstrate their performance. And the resulting performance in tests that are common with the in-person are now directly comparable because now they are single-shot tests. And they can together be considered for the best-in-class runs. Of course, we can't run the finals, the overall finals online like this because the whole maze isn't necessarily available to every team. And so only the in-person teams are eligible for the championship finals. So that's the end of the logistics and the rules and introduction. I'll now talk a little bit about the project within which the Robotically Manufactured Robot Challenge and RoboCup Rescue fits. And this is the DHS NIST ASTM International Standard Test Methods for Response Robots project, based out of the US National Institute of Standards and Technology, just outside Washington, D.C. Where do we start? Well, the problem is that before the project started, there was a lack of coordinated innovation and commercialization within the space of response robots. It was difficult to assess the performance because there were no standards. The robots were not addressing end user needs because these were not being communicated. There was no mechanism to communicate these operational requirements through standard tests. It was all fairly abstract. There was no structured training to improve proficiency that was universal. And there was no credentialing. So the standard test methods developed by this project need to be this method of communication to promote innovation, to enable users to understand the emerging robot capabilities, to put the students and the manufacturers on the same yardstick, to guide robot purchasing, acceptance testing, and deployment decisions to make sure that the best robot is being deployed. Because after all, the best robot in the world used for the wrong purpose is indistinguishable from the worst robot in the world. And then to focus training and measure operator proficiency for credentialing. So NIST is US-centric, so these organizations are mostly based in the US. But the idea is that we have these all interested stakeholders coming together to develop and refine the tests. There are facilities worldwide. This is actually a slightly out-of-date list, and this is just the research, active research and development and event facilities. We also have facilities all around the world. So Sydney actually has Sydney has a facility and Brisbane has a facility now. And then individual response organizations, firehouses, police rescue, so on, they all have their own facilities all around the world that aren't even being mentioned here. So our approach is to develop test methods that are representative, repeatable, reproducible, science-based, and inexpensive. The idea is everyone should be able to build this. As much as possible, our standard test methods, and by extension, all of the arenas, should be able to be built with what you find in a normal hardware store and a normal stationary supply store. Enable innovation through competitions like RoboCup Rescue to identify and communicate gaps in performance and to measure the performance across more than 50 tests in the normal suite. And to help different users and robots. So different users have different benefits, and we've gone over some of this already. So a whole spectrum of available test methods. They range from standard test lanes, such as what you see in RoboCup, through to things that we can embed in scenarios, in more operationally relevant areas, which are less standardized, but at least you're performing a standard test in a non-standard environment, and you can determine how that environment affects your score. We have test lanes at different scales, and in addition to ground robots, we also have aerial drones and underwater robots. The commercial robots being deployed, we range from the very small, this is a 20-centimeter grid, right through to very large robots designed, to vehicle-sized robots. We'll note that we have commercialized robots that have previously shown up in RoboCup. 2006, this Telerob Telemax showed up to RoboCup, got an award, one of the technical awards, got commercialized, and is now one of the most successful response robots out there. Objective evaluations measure the differences, and these are measured in a suite. This is like going to the radar charts, where we have different tests, or in this case, together measuring the ability to go over terrain. So you want something that can do well across all of these if you want an all-round terrain robot. But you can also look at these individually. Maybe I'm very interested in step fields. I always go through very rough terrain. Well, while Robot H here might be doing best overall, Robot G does the best in the step fields, and maybe that's the one you want to get. This allows you to make these decisions with a lot more nuance, or at least allows the responders to make these decisions with a lot more nuance. But as researchers, it also means you can highlight good performance in your specific area, also with a lot more nuance. It also allows us to generate graphs like this, which mean that we can highlight, we can develop thresholds for performance. So this is performance. You don't need to worry about the individual words here, but these are performances in a suite of tests for bomb squad and hazardous materials robots. And you can see, and the orange bars here are the manufacturer's expert on a few different robots, and the rest of these are users. And you can notice things here, such as where the average is, what level of performance we can expect, but also where some robots have performance in the hands of normal users that surpasses the best manufacturer's performance of other robots. You can get very different levels of performance from different robots, but it also allows you to determine how quickly you can train up to these. If a novice on a robot A is getting better performance than the expert on robot B, then you know that there's something that robot A is doing right. Outreach to responders. So the standard test methods help answer essential questions for the responders. The bomb suits don't really help much. We don't want to have the responders have to go up to these packages, but they also want to know that the job will get done. So what we do is we actually have robots and responders running through the same tests. This allows them to relate the performance of the robot to their own situation, to their own experience. They can go, oh, okay, the robot is having trouble here, but for me to do this, I'd have to be lying on the ground looking up, whatever the case may be. These bomb suits are very hard to move around in. So this standardized testing has a way of communicating to the responders the capabilities of the robot that are very, very meaningful to them. So start remote, stay remote, mission success has both the robot system capability and the remote operator proficiency as part of it. And the system capability can be a little bit interesting. For example, one of the capabilities that's required is breaking glass, getting into buildings, getting into vehicles. Traditionally done with a ground robot, actually using a glass breaker. But now you can have emerging technologies running in the same test. For example, drones with glass breakers on them. They can perform on the same test and allows responders to actually see what the difference in performance is and maybe figure out that the new technology is what they want, or maybe it doesn't do their job. We can also adapt the test methods. This is the Quince robot, the view from the Quince robot within the Fukushima nuclear power plant. This is actually a robot that was refined over many years of the RoboCup Rescue Robot League competition. And it was the first robot to get to the top floors of the power plants and was critical in the shutdown of the nuclear power plants after the Fukushima Daiichi nuclear power plant disaster. It got up to most of the floors, but it got stopped by debris on the stairs because this hadn't been tested. We've adapted the test methods, and in the competition and in the standard tests, we now have standardized ways of blocking the stair with debris to measure performance over this kind of scenario. And we now have robots that can tackle this because we've now adapted the standard tests. What other tests do we have? Well, we have things like underwater robots. These are very similar. We try and reuse the same principles across all the modalities. And these will be very familiar to those who have come to RoboCup in the past, including the mapping and the manipulation. Of course, instead of terrains underwater, we have water jets. We have pumps that are pumping water currents into where the robot is, and this takes the place of the terrain as a challenge. We also have aerial robots, small and large, in this case, instead of having the course that you drive back and forth on, we have positions in space that you traverse, that you go through in a specific order, and these spaces are denoted by these buckets. 2 buckets line up, and they so if you're in the right position, you can see into both the buckets, but anywhere else you can't. The idea behind this is you can test yourself, and you know where you are in space because you know what you can see. You don't need any other equipment, you don't need any other localization, you don't need any other proctor around to know that you got to the right spot. These can be run pure like this, or you can embed them into vehicles, structures, and the like. Particularly relevant for RMRC is we're tackling this at small scale as well for indoor robots. I know there has been some interest within RMRC to do drones, and we hope to be able to bring this to the RMRC at some point soon as well, both flying in sort of indoor but not so confined environments, as well as truly in confined environments within the arena itself. And then, of course, there are sensor tests both within the buckets themselves. So once you got into the right position, can you see inside? But also more pure sensor tests like the readiness tests. We have, and instead of having a line to drive up to, we also have buckets that if you're in the right spot, you're looking right into them because they're all pointing to the same place in the sky. We also have the same QR codes scattered around the environment that now are measuring the ability of robotic surveys, aerial surveys, to go out and inspect the entire environment, and we can measure automatically and to statistical significance the ability to observe these codes, which gives us the ability to say what percentage of the environment the vehicle inspected at what resolution. So in summary, the standard test methods communicate these critical requirements and capabilities used by researchers, manufacturers, and users. The Rescue Robot League is a critical part of this process, and the Rapidly Manufactured Robot Challenge makes this research driver accessible to a wider audience, including high school students. Anyway, so that's it from me for the prepared remarks. Please visit our website, comp.oarkit.org, to learn more and to join up. We hope to get many more teams this year, both online as well as in person, particularly from within Thailand. We know that Thailand has a very, very vibrant rescue robotics league and national competition. I believe you have like 100 teams, something like this. I'm sure some of these teams have inspired high school teams. Well, high schools, this is your opportunity to get involved in the World Championship in your own country. These arenas are very easy to spin up. We've had teams spin up from high schools in a matter of a couple of months. The arenas are very easy to build. The robots are very easy to build. You should be able to get something working very rapidly. So it's definitely not too late to get started for this year's competition. So we encourage that. Anyway, that's it from me. So back to you, Verichai.
Okay. Thanks a lot, Professor Raymond, for your wonderful and informative talk. Very exciting. Any comments or questions from the audience? You can raise your hand, or you can maybe type in the chat box. Don't be shy, please. I guess right now in Thailand, high school is busy for their incoming exam.
Okay, well, so
actually in March to April, they're gonna March to May, it's gonna be like a school break. I think that might be a good time for them to form a team.
That would be wonderful. So we actually, if you go to group.oarkit.org, join our mailing list, ask questions there, introduce yourself for the new teams and for the teams who are watching this on the recording. Not too late to join. Send us some email on the mailing list. Declare what you want to declare your interest. Build the arenas; they're very cheap to build, and make a start. And they're very useful in the classroom as well.
Any question? I got a couple of questions.
Sure.
You didn't talk about the communication during the test. What kind of communication between the robot and the operator? They gonna be like wide or wireless, or can be both, or any restriction on that?
So of course we like wireless communication. The problem is we also have some competition logistics to deal with, and the fact is that in the RoboCup arena you have a lot of robots using a lot of spectrum. So we allow teams to use wired tethered communication just because we're one of the leagues that is actually possible, or it's possible to do that, whereas it's a bit harder for the soccer robots. So we leave some spectrum for the soccer robots to run around in. But you're right, ideally they should be radio. That is something we generally don't test in RoboCup just because we are operating in close proximity to many other competitions.
I see.
But we do actually have standardized tests for radio communications more generally. Those are performed away from critical infrastructure and from other things where radio is necessary just to avoid interference.
Okay. And is it possible that you're gonna have like a surprise test bay, or maybe surprise mission?
I'm sure there'll be some surprises. We'll have to see. We'll have to see what the surprises are. Of course, and there are surprises in terms of some surprise tests that will spring, but also the layout of the final arena will be a surprise because it's going to be constructed at the time.
Like if there like some surprise mission, and they have to design the tool at the site and maybe fabricate the tools, or maybe improvise something to achieve the goal or something like that.
So that may be necessary.
Is that possible?
Yep. So one of the things we focus on is that the robot is a particular configuration, because you're performing each of these tests and the tests represent individual capabilities. You should really perform each of these tests using the same robot. That way you can put the numbers together. What we don't want to have happen is you do one robot for one test, another robot for another test, and you try and combine the scores and say, look at what we did, because that doesn't represent the performance of one robot going through the test. Remember, all of these tests are supposed to be put together to represent a mission, right? If the mission involves going up the stairs and then turning a valve, you can't test using your valve turning robot and test using your stair climbing robot and then expect that to work, because the robot that goes up the stairs isn't the one that can turn the valve, right? They need to be performed with the same robot for those tests to be put together to be meaningful. Having said that, you know, maybe we can have some challenge in there, which requires a little bit of adaptation, understanding that that's not part of the same competition and not part of the and not done with the same exactly the same robot. You may have had to modify the robot, right? Because the other thing, right, you have to modify if you have to modify the stair climbing robot to do the valve turning in the competition, that's a problem, because in the real world, you can't drive up the stairs and then have someone up there with tools modifying the robot to allow it to turn valves, right? This is downrange.
Maybe you can carry 3D printer with us in the field.
Well, carry a 3D printer with you. So yeah, but no, we can certainly have challenges like that, but not within the standard test part of the competition.
I see. Yeah.
Maybe in the finals where everything is sequenced. So now you can't touch the robot between when it starts and when it ends. Maybe we can do something there, perhaps. I don't know. We'll see.
Okay. About your proposed test method. So I think in the future, it might be some kind of certification for the robot vendor or something like that.
Yep.
Yeah. Cool.
So we're not certifying anything. So when I say NIST, you know, if it makes sense, so we develop the tests, right? We develop the measuring stick. It's up to other organizations to determine what level of performance they require for their certification, because different organizations and different applications require different capabilities. We help them figure out what those capabilities should be, but we don't determine what those thresholds and which tests are relevant. They do that. We develop the ways of measuring them. So in RoboCup, when we figure out which suite of tests to bring each year, we go back to the users and go, well, what is missing, right? What capabilities do you find missing and that need to be tested?
So like that, you give them the numbers and they have to assess by themselves, right?
We give them the way of measuring the number, right? We're also a test development facility. We're not a testing facility. We're a test development facility. So we have facilities all around the world that do the testing.
Okay. So they have to do the testing by themselves? Right?
They can do it by themselves. And the idea is that everything is cheap and easy enough that they can do it by themselves. Or they can go to one of the professional organizations that does this testing.
Okay. Very cool.
We do enough testing to make sure that the tests are working.
Okay. From the audience, any questions?
How much audience do we have? Oh, we got a few. And of course, I'm assuming this is recorded. So so this will be available, I assume, to prospective students as well. We do need to have people tell us if they're interested in the next week or two, because of course, internationally there are some challenges at the moment, especially for schools that need to set their policies now. But we are hoping we can get some good domestic interest as well in this. Please do let us know soon.
I have discussed that with the team. So let's see how can we go from there. I guess one more quick question. Is there any restriction on number of teams per country, or just open? You can register any teams per country.
So for the online competition, we don't care, because it scales, right? There's no team number limit for the online competition. For the in-person, it depends on how many teams we get overall. For major, we generally limit it to 5 teams per country or region. But we can we're going to see, it'll probably be 3 to 5 teams, but it depends, like the local country. So within Thailand, we can be a bit more relaxed about the limit, because it's the domestic competition, right? It's the local competition. So that's a call we make once we know who's participating in the physical competition, in the in-person, or once we know who's interested.
Okay. Yeah. Any more questions? I think that's all for tonight. So I think that's it. So I want to thank everyone for joining us for tonight's talk. actually it's very short but very informative seminar, right? And I hopefully we can physically see each other in Bangkok in
Yes.
June, right? April, June or July. June, right? So it's, around 6 months now. And for tonight, I think that's it. And I hope everyone are safe from COVID. And hopefully
Stay safe.
see you.
11th to the 17th of July.
July. Okay, July. So we
But
still have
yes,
some time to
please,
fly.
everyone
Okay.
stay safe and get your vaccines, wear your masks, and hopefully we can all meet.
Yeah. I think in Thailand, maybe at least 70% of population get vaccine already.
Oh, that's good.
We three dose already. For myself, 3 dose already. So
Good.
I think that should be safe. Hopefully, no more variants.
Hopefully, no more variants. Yes, indeed. Yes. Thank you again to Verichai and Panavi for all your work.
Okay, thank you very much. Enjoy your day or night, depends on your time zone. Okay, thank you. Goodbye.
Bye.